Right. So here we're going to look a little bit at the idea of the static equilibrium and the idea of stability. So consider I have this table here, and it's got two legs, and all I'm doing is setting some board on it so that the board just sits there. Now, here's the thing. If I take a weight and I put it somewhere, so I have put something on my table, well, depending on where I put this is going to help determine how much the individual table legs have to support in terms of the weight. So for example, if I put the weight here, both of the legs have to support some of the weight, but more weight is here, but this table leg has to be supporting more than this one does. And even though the weight is physically sitting on top of this one table leg, this one still has to support some of this weight, because the weight of this thing is, is still acting on this entire system. Now, here's the thing. It turns out that if I go further and further out, more and more of the weight of this object here is supported by this table leg compared to this one. And eventually, I should be able to push it far enough. So there's a point after which the system becomes unstable, because now instead of there being enough weight over here due to the table to keep the table from flipping, now the weight has moved past this point here, and so now we're sort of right at this tipping point. All of the weight of this object is being supported by this table leg. As you can see, none of the weight is being supported by this table leg, and we move ever so farther beyond that stability point, the thing tips over. So what we want to do is we want to set up the equations to be able to determine, okay, suppose I have this table, and the table itself has a certain amount of mass, it has a certain center of mass that we can locate. We place our table legs at some location, a certain distance apart. How far out can an object move before the system here is going to tip over? And so we're going to show this calculation in two different ways. Because the reason we're doing it in two different ways is because when it comes to writing down the expression for the sum of the forces, there's really only one way we can write that. But because the torque expression is the torques based on how forces are acting relative to a pivot point, as I'm going to show here, we can pick whatever pivot point we want, whatever point on the system. We can say everything's rotating relative to that. And even if we pick the wrong physical pivot point, the math will still work out and tell us how the system would behave. All right. So trying to give you an idea of this, consider here I have a table set up, and it's got two legs, it's got some board, and out here is going to be the mass that's walking further and further out, here represented by a cat. To indicate a few things here, we're going to assume that the board is going to rotate relative to a pivot point that's located right at where table leg A touches the table. This open circle here is where the center of mass is. And then that means we have to define three distances. One is the distance from this table leg to where the cat is. One is the distance from this table leg to where the center of mass of this sort of plank of wood is. And then another length here would be the distance from this table leg all the way to this one. So we don't want this table to fall down or flip over. So we're going to set up the condition for static equilibrium and rotation equilibrium. So the sum of all the forces acting on the table are, I got the two table legs pushing up on it. I got the weight of the plank itself pushing down, gravity pulling down on this plank. And I got gravity pulling down on the cat, who in turn is pulling down on the plank. So the four forces acting here are the two table legs, and gravity is acting on two pieces of mass. And that tells us everything about the forces acting on our entire system. What about the torques? Well, remember, for us, torque as an expression is given by how far we are from a pivot point that the force is being exerted, what is the size of the force being exerted, and what is the angle between the direction the force is being exerted relative to the direction to the pivot point. Well, in this case, this is easy again because we're going to say that these are the distances from where the forces are being exerted to the pivot point, and these are the directions of the forces, up and down. So that means the angle between this direction from where this force is, fixing this cat, and to where the pivot point are, that's an angle of 90 degrees, and so for all of our forces here, we just have to use this expression. Now, if we take forces that cause us to try to move clockwise to give us negative torques, and forces that try and cause us to move counterclockwise to be positive torques, then that means here, this cat, negative, because he's trying to make the system rotate like this. He's a distance of RC away, C for cat, little m, because that's his mass, and G, because it's the force that he's exerting is his weight, trying to pull this thing down. Over here, we're going to call this board, this table, we're going to use P, it's just a plank of wood. So RP is the distance here to where the center of mass is relative to this table leg. This here, this mass of the table is trying to make the whole system rotate this way, which is counterclockwise, and so that's positive. The table has a certain mass, and G, because again, the weight is what's exerting force. And then over here, we got the table leg. Now note that this table leg is pushing up onto the table, right? Up onto this thing. So because of that table, the force due to this table leg is acting as if it would, if it could act freely, it would cause the system to rotate clockwise. So we got negative. This time, this distance away here, because it's just B, will be noted as RB. Note this time we can't replace the force with M times G because whatever this force is, it's just the force being exerted by this table leg onto our system. So we have these two expressions, and we look at it and we say, okay, we ultimately, in this part here, care about what is the maximum distance this cat can walk away from sort of this table leg and not have the whole thing fall over. So we look at our two expressions and we see, hey, this one gives us a way of being able to solve for that RC value. So we do that. We move our quantities over. And so now that we have an expression here, this expression combined with this expression would hold for all the places we could put the cat that's closer in relative to the farthest point he could be at. So if we put the cat right here and we calculated, we knew what distance he was, we could go back and calculate the relative amounts of force that the two table legs would have to support, and this expression and this expression will both be satisfied. However, with our discussion of stability, we're making an assumption. We're assuming that the cat is going to walk out to some distance such that the force being exerted by this table leg goes to zero because this table leg is no longer interacting with this thing at all. So that means from our expression here, we could say, well, that for the force to the other table leg would have to go to zero, which would just become zero in this expression. And then what we're left over with here is this expression for this length, the mass of the plane. We got some accelerations due to gravity, but they can cancel out. And lo and behold, we can determine here that based on whatever this setup is, how far this cat can walk out from the edge of the table can be known in terms of where the center of mass is of the plank that he's standing on relative to this table leg. So that's one way of going about and solving this problem. Now let's restructure the problem. Let's say we want to pick a different pivot point and still run all the calculations and see what we calculate. So now I've hidden the table legs and replaced them with just these upward acting arrows because I needed space down here. This time we're going to pick our reference point, our hypothetical pivot point, as being over here where table leg B is. And then that means we have to redefine all of our distances when it comes to talking about the torques. So here I have RCM for the distance of the center of mass of this plank to where the pivot point is, or the assumed pivot point. Here RA is going to be the distance from table leg B to table leg A, and here RF is going to be the distance from this table leg all the way to where the cat is. F here is going to be for feline to distinguish it from cat over there. The expression for the sum of the forces, turns out that expression hasn't changed. When it comes to the torques this time, well, we measure everything relative to this point. So the plank itself is trying to make, the weight of the plank is trying to make the system rotate clockwise. So at the certain distance away, for a clockwise rotation, that's the negative, there's the mass of the plank exerting that certain force. Then at this distance, there's the force A to the table leg A. It's a distance RA away, and it's got a positive because that force is trying to make the system rotate counterclockwise. And then similarly, the cat is way over here. It's a certain distance away. His weight is trying to make the whole system rotate down. So we can then take this expression and solve for, okay, what is going to be the distance the cat could be at, RF, based on the, what else is in this expression. And so that gives us this. Now, this expression on its own, well, just like before, this expression and this expression, both, if we place the cat at an arbitrary point and we measured, where the cat was located and what the forces were, then this expression and this expression would both simultaneously be satisfied. However, we again care about the farthest possible distance that the cat could be, in this case, all the way from table leg B way over here. So, turns out that, just like before, B, the force at B to the table leg B would have to be 0 to give us the farthest possible distance. But in this case, our expression has FA. So what do? We go back up here and say, well, if I use this expression and I set FB equal to 0, then FA would have to equal just the mass of the board times the acceleration due to gravity plus the mass of the cat times the acceleration due to gravity. And so now I have this expression over here that tells me how far, what is the maximum distance that this can be in order for this system to not tip over. Now, first off, these two expressions are all talking about the same system. So notice that, like the value RC up here, if we looked at the value RF and the value RA, the length here RC is equal to RF minus RA. And similarly, the RP value is equal to RA minus RCM on this. So if we took this expression and substituted in these values, we would get out this expression. So these two things both talk about the same system, but one's talking about the distance the cat can travel relative to this point, and the other is talking about the distance the cat can travel relative to this point. What makes this expression here potentially useful is because here, since it measures relative to this side, here if we know where the center of mass is and we know, like how long the plank is or how far we want to have the thing move relative to this point, that expression gives us a way of being able to solve that compared to the other one.